17 goals for sustainability were created by the United Nations at an aim to provide prosperous and sustainable futures for all the countries of the world. Our team's focus was on Goal 6, to ensure the availability and management of sustainable water and sanitation for all. Water is essential to life, but for many First Nations communities in Canada, access to safe and clean drinking water is a daily struggle. That is why our team has developed an innovative solution to address this critical issue. After conducting extensive research, we decided to adapt and combine two existing water filtration methods, microfiber filters and UV filters.
After evaluating the needs of our stakeholders and end consumers, we analyzed our research and found that polymer hollow fiber microfilters were proved to be the most effective in a rural setting that we were designing for. Microfiber filters are commonly used at a small scale in the current market for backcountry water filters such as the LifeStraw or platypus filters. Hollow fiber membranes are a polymer-based hollow fiber structure that contains nanoscaled pore sizes, scaling down to sizes lower than 0.2 microns. This allows them to have a highly selective filtration rate and optimized performance at standard household water pressure, which is better suited for the needs in this design phase. Although the filters have a high filtration rate of all particles and ions within water, our design does not filter out small bacteria and viruses at the operating pressure. To solve this, we decided to integrate a UV sanitation device into the system. This would filter out all particles, bacteria, and viruses to optimize our health performance. With these aspects up to spec, we then combine the two technologies into an integrated household device that is meant to be installed directly into the main household water line. This would supply pure filtered water to all outputs within a household. Considering the sustainability of our system, we opted to use bio-based plastics and low energy consumption UV devices. This lowered the overall lifetime impact and eco-cost of each product we make. This then carries forward to the end consumer to provide a high-performance, affordable filtration system.
We wanted to make a works-like prototype which would allow for testing flow rate, leaking, and effectiveness. But this was not feasible to create physically, so we combined our research with a looks-like prototype to compensate for the lack of resources. Based on our cost-benefit analysis, our solution would benefit the equivalent of $429.80. Our in-home water filter has the potential to change the lives of many First Nation communities by providing them easy access to clean, sanitized water without the reliance on the Government of Canada to provide large-scale repairs to water treatment facilities. Finally, this represents a major step forward in addressing the water crisis for Canadian Indigenous communities.
Here are some 3D models of some iterations of our design. This first design would require flexible pipes in order to open and close. This design integrates the UV directly into the filter with a clear pipe allowing the UV to sterilize the water. And this design flips open to allow easy access to the filter for maintenance or replacement. This model we took into a looks-like prototype by 3D printing it in order to test the fit and functionality of the connections and the hinges.